Salutations, fellow chemists. So today we're going to be looking at alkenes versus alkanes. So in my pocket here, I have an alkene. So this is ethene. And in my other pocket, I've got lots of molecules in my pockets, you see. And this one here is our ethane. So what's the difference between these? Very quickly. First thing you should know is the general formulas are always very, very different between alkanes and alkenes. Alkenes, you should remember, is CnH2n, where N represents the number of carbons in our molecule. If you look at alkanes, it's going to be CnH2n plus 2. Okay, before we move on though, I'd like to make it very clear we're not looking at alkanes today. I just wanted to use that as an example and so we can make a nice comparison. So I'm going to get rid of this for now. And the general formula as well, we don't need that anymore. We're looking at the structure, bonding, and reactivity. Excellent. So before we move on, you need to know a few definitions that will be very useful in terms of understanding all of those principles of alkenes there. First one, you need to know what a sigma interaction is. So that's the symbol for sigma, lowercase, and that's the symbol for pi, lowercase as well. A sigma interaction is just an interaction between atoms. A pi interaction is an interaction above and below atoms. And an addition reaction is when atoms or groups add to a molecule to form a larger one. So let's have a look at the structure of alkenes now. So for an alkene, you have 2 carbons. I'm just using R to represent any alkyl group here. And this is the sigma interactions just displayed over here. All I'm showing you are the interactions between the atoms. However, you know that every carbon has the ability to form 4 bonds. So if you've got 1, 2, 3 bonds, then that means there's an electron left over. So above and below here in our p orbitals, I'm going to represent electrons like so. What you actually do get now is, finding my pen, an interaction happening above and below. So I've used the red to signify there. So that is now a pi interaction. So in an alkene, you have the sigma interactions and then you have the pi above and below as well. I'm going to show you a different diagram here, which shows you the resultant. So that is our sigma again. And I'll represent this as R dash. 1 dash there. And you get a cloud above and below, like so. What does this mean? So first thing this means for alkenes is, number 1, there is an area of high electron density. I represent electrons with E minus, but do not do that in your exam. Make sure you write out electrons fully. But we have high electron density above and below here. That just means the electrons are concentrated in a small space here. There's a high probability of finding electrons there. What that means is it makes these susceptible to electrophiles coming in. So electrophiles are attracted, and they're attracted to the area of high electron density. Number 2, what this means is you end up having addition reactions. So we looked at that happening before. There'll be a video coming up soon, so watch out on the YouTube for addition reactions and the addition reactions of alkenes. But all that means is because we have extra electron density around our carbons here, there is space for more atoms or groups to come in and add into our molecule. So addition reactions, you always think about alkenes when you are thinking about addition reactions and vice versa. And then the last thing, number 3, is to think about the isomerism that happens as a result. So here we end up with isomerism. And I'll show you again with our models very quickly what that means. So back to our alkane. This is the alkane. You can see the alkane's free to rotate around here. That's great. However, for the alkene, where we've got the double bond now, it's very difficult for me to try and rotate that. And the reason being is because, if I label these again for you, we have our sigma interactions. I'll actually go for the one in between the carbons. So that's a sigma. My pen is dying there. And then above and below, we have our pi. So that's a pi, put pi bond and sigma bond. And the pi bond just means that the carbons do not want to move around from each other because that will cause these p orbitals to come out of sync. So if I use my fingers to show you, that's the p orbitals in sync. If you move this away, then it's very difficult for them to actually overlap. So they don't want to rotate because the p orbitals need to overlap. So very quickly, let me just write this here. That's because of the restricted rotation. Okay, perfect. So that is the end of the video there. I'm just going to very quickly recap for you. What we need to understand is for the structure of alkenes, you've always got a double bond where you've got a pi bond and a sigma bond. Together, they make the double bond. And what that means is in terms of the bonding there, we've got the double bond in between the two carbons, pi bond above and below, sigma in between, and then sigma bonds for the other groups around. And this then leads to the reactivity of the alkenes in the sense that they are attracted to electrophiles due to high electron density between the carbons. And that then leads to the fact that we can also have isomerism because of that restricted rotation there. So hopefully that's helped you to learn a lot about alkenes and why they're different to alkanes. And there will be more videos coming up soon. So make sure you like, subscribe, and smash that bell button.